Next, we have Shawn Slavin. Shawn is Senior Systems Analyst with High Performance File System Team at IU. He has a background in parallel programming and astrophysics. He holds a PhD in astronomy from IU. Ladies and gentlemen, Shawn Slavin.
Hi there. Did anybody happen to catch some of the cool equations on that last slide? I know I saw Newton's equation, I saw Ohm's law, and there was some other good stuff in there. Anyway, I wish our slides had those, but also I didn't know when I mentioned that I had a degree from IU that was going to come after Rob's discussion about the Venus statue. So I have 3 degrees from IU. I have no knowledge of anything that ever happened other than that. Yeah, she's still there though. Okay, so today I'm here to basically talk to you about a use case, and the number of people on the author list is kind of big because there's a number of people that have been involved in this. Tyler Balson, Yue Lee, and Professor Adam Ward at the top here are all associated with the SPIA, were associated with the SPIA program at IU. So Tyler's here today. I'm not sure if Adam is in the room or not. Cicada, Dennis, Robert Herschel, and Steve Sims and I are all associated with UITS, and Holger Brunst is a collaborator of ours who's in Dresden. So the application that I'm here to talk to you about is a program called Agro-IBIS, or initially just IBIS. The background on the application itself is that it simulates agricultural fluxes and variables associated with inputs from atmospherics and geological and agricultural land management data. So the agricultural land management topic is clearly one of ever-increasing complexity. So there's only so much farmable land within certain parts of the United States, just as an example, and how that gets managed is a topic that is becoming more and more challenged by the many people who are stakeholders in that. We have increasing demands on crop production that come from the fact that we need to produce more food for more people. It's a huge part of the United States economy. It's a large part of other economies around the world. And being able to come up with best practices based on the many variables that impact the land use is a challenging problem to solve. So the application, the Agro-IBIS application, is one that makes an attempt to simulate these processes using I'm trying to remember the term. It's an Earth model. It's an integrated Earth model that involves inputs from a variety of sources and then simulates the processes in a time-stepped fashion, much the same way as you would step forward a much simpler, say, physics problem, trying to figure out the trajectory of a baseball, under the influence of several different forces that are at play in time. You've got boundary conditions, which can change over time, and do in this case, and you have quite a number of different processes that are happening at the geological and hydrological level, at the plant growth level, at the atmospheric level, both in the vicinity of crops, and then of course the input from rainfall and sunlight and wind fields. So the Agro-IBIS application itself is the one which is the topic of the talk. It is being used here at IU by Dr. Ward's group, primarily because it's a widely validated model for a region of problems that his group would like to look at. The code itself is originally a serial Fortran code, much as you might have seen written for, a PC back 20, maybe even 30 years ago. The code itself does date back to the 80s, and that's interesting in its own right, because it has caused a number of challenges for us as it's been adapted to run in parallel. And so that's really the point of this talk, is that simply parallelizing an embarrassingly parallel, or as I like to call it, massively serial code, is, it can be very valuable, of course, but if one doesn't take into account the I/O patterns that the code produces, then a giant, computing machine like a Cray or just a very large PC cluster could easily crush the file system for other users. So in this case, we have an application that's, by itself a standalone community-based, or a standalone application with a community code base that the researchers here at IU are not particularly interested in modifying because of the community code base and the fact that they're not necessarily actively developing the code in a way that would make major wholesale changes at any one time. And so the way that this code works internally is, for the most part, been left alone with minor modifications here and there, with the idea that it's a tool that they can use to produce models that can be analyzed after the simulation, as opposed to a code which can be developed to produce simulations not just here but also elsewhere. And so the attempts that were made here to parallelize the use of this code largely rely on codes to wrap this compute process so that it's effectively isolated from the other versions of itself running elsewhere concurrently. And I included this diagram just to give you an idea that, it's a somewhat complicated process that's being stepped forward in time here. And you can tell that, some of these modules that are listed both feed back into, or they both feed forward, but also receive feedback information from the modules that they feed into. So if you can imagine a situation where you've got a set of equations where you, in order to come to a solution at any one time, you have to iterate to get to a solution. And then once you've gotten to the solution, you now have the initial conditions to make that next leap into the next moment in time. That's the sort of thing that's happening here with Agro-IBIS, and the models that are used as the test case, the sort of canonical test case, are a 60-year simulation of agriculture in the Mississippi Valley Basin. So this is agricultural inputs and outputs being modeled over 60 years for a huge region of the central U.S. using historical data and then simulating stochastic results based on probabilities for things like rain and light and that sort of thing. And so at every point in time in the simulation, you know, the overall time-based loop cranks forward, and I should say at every iteration of the loop, it's deciding whether or not it's time to kick out some more output. And there are various frequencies at which, you know, the code can produce output. And they're the kinds of frequencies that humans are familiar with, like weeks, months, years, that sort of thing. And so, of course, you can kind of lay back and say, okay, well, we're only going to take output at, say, yearly intervals, but that would only give you yearly averages for your results. So in order to get high temporal frequency results, we need to be able to do outputs at more frequent intervals. So this is one of the motivations for going to a parallel application of this code, is to be able to put it on a large number of processors, to run it concurrently, and use a wrapper code to both do the domain decomposition for the problem by effectively chopping up the areas in which these simulated processes are supposed to happen, and putting them each into little computational nuggets of the Agro-IBIS Fortran code, and then cranking them forward in time until the simulation's over, and then stitching all of those decomposed zones back together. And of course, the whole idea makes me kind of jealous in a way, because not many processes can be modeled this way. Most processes, you know, if you cut them up, they involve boundary conditions and all kinds of data exchanging that needs to happen between each time step so that it looks like you're modeling flows across cells, and we don't have that. So in some sense, this should run in a kind of, I don't want to say mindlessly easy way, but in a trivial way that should produce output basically as fast as the cray that we have here can produce it. I don't have a slide on that, but we have a cray here on campus that's, you know, a combination of 344 dual Opteron nodes. So that's a XE6 model cray, coupled with 676 XK7 nodes, which are single Opteron plus GPU modules. And each of the Opterons is 16 processes, or 16 cores on it. And the reason why that's relevant here is I'm going to show you a couple slides in a moment that that will show, you know, kind of a breakdown of the performance of this code. And the way that the computational wrapper that was written in C++ to kind of manage all of these processes, the way that that was written is as an MPI application that basically launches each of these IBIS invocations with a system call. So no communication whatsoever, just go run to completion, and then I'll clean up the data that you've produced and stitch it all back together for you afterward in a post-processing step, which that alone, you know, produces a fair amount of work for the overall process. Because of the way that that's set up, and because of the memory management that we have on the nodes versus the amount of memory that has to be managed by both the MPI part, the C++ wrapper part and the Agro-IBIS part, we're really only able to get 16 processes of Agro-IBIS running efficiently at any one time on each node. So that forms the basis for a couple of important points later on, like what is the quantum for, you know, a result with this code. So I'll explain that. In terms of improvements that were done to the code prior to me being involved with this project, which is about a year ago, I came into this project because we found that there was one particular user who was really hitting our main file system, the DC2 file system that was mentioned earlier today, hitting it particularly hard, and it was effectively causing everyone, including that user, to have a negative experience with I/O. So those improvements would be the use of netcdf, which is a standard library. Many of you in the room have probably heard of it or have been involved in using it at some point or another. It's basically a way for packaging up data in a format that allows easy retrieval for variables based on latitude and longitude. It gets used a lot for remote imaging, remote observing, satellite data, that sort of thing. And of course, it makes for the perfect container for data in a simulation like this, where everything is based on land coordinates overall. And then the parallel wrapper that was already written was written by someone outside of UITS. So there's a group of us from within UITS that sort of came together to try to help undo this I/O problem that we were seeing, and also to be able to help Dr. Ward's group achieve the kind of results that they had been hoping for in terms of just runtime. So as I mentioned, the application was initially parallelized without much regard to the impact on the file system, and that makes some sense, really. I mean, you're looking at a simulation or a code for a physical simulation, and you're saying, okay, am I making sure that I'm chopping up the problem correctly? Am I missing data? Are the results coming back after I stitch it all back together? Do they match what I get in the serial run with the original code? That sort of thing. Once you get to the point where you're confident in that, you think, okay, well, I'm good to go. So if it has to create twice as many or 10 times as many intermediary files in the process, well, who really cares, right? Because there should be a file system behind all of those processors that can suck up all that data and that can spit it all back out when I need it. And in some sense there is, but it turns out that there are things that you can do that will cause people who've spent a lot of time trying to intelligently engineer the file system to be able to handle the data rate. It will cause them to want to pull their hair out because they didn't count on you doing some things that you don't even know you're doing. So I'll explain. I guess I mentioned about the MPI wrapper here that runs the overall Fortran code. So the one very easy way that you can tax the file system is to wrap all of your calls to write data, no matter how small a chunk of data that is, in a routine that will open the file, write the data, and close the file. And then just do that a lot. And then take that a lot and multiply it by, 512 processors or 1024 processors. And it turns out that will cause, at the very least, will cause the MDS on the Lustre-based file system to become very, very busy and hot and unhappy. And so that's the very first thing that we tried to deal with on this. And then there are some other issues too, like when you do parallel computing, you want to try to keep as much of the intermediary I/O as you can local to the machine. And that's kind of rule number one of HPC programming, is that whatever you can keep local to the machine until you're done, until you have a result, that's what you do. And how much of that I/O is done with message passing and how much of it is temporary file storage all depends on your strategy. So at any rate, it turns out that with the cray that we have, that's a bit of a challenge because we don't have local drives on the cray that we can access to do that sort of temporary storage. So just to put some numbers on DC2, we've already seen a slide of it today, but it's a 5 petabyte file system. We'll pretty soon hopefully have that Lustre version upgraded to 2.7, but at any rate, at the time that this has been in development, it's currently at 2.16, which is in part relevant to some features that we'd like to be able to make use of, but that's it is what it is. It's also a very busy file system, so we have a lot of users that are particularly interested in getting their own work done. And so the file system is backed by 16 OSSs, 252 OSTs, and it's served by 56 gigabit IB, and it serves both as our compute scratch and our somewhat less ephemeral project storage for people that are working on projects that are going to go on for more than 60 days. So the initial challenges of dealing with a parallel version of this code, are basically trying to find a way to keep it from beating up the file system. And there are two things that we did to make that go initially. One was we found a way to get it off the file system and put it on a different file system, which I'll explain in just a moment. And the other one is to try to reduce the number of unnecessary I/O calls in the code. So when we looked at I/O bottlenecks in the code, just by running some test cases during a maintenance day when the rest of the file system was quiet and there was not as much of a challenge getting plenty of nodes on the system to do testing, we saw that we had IOPS numbers that were peaking for those runs at about 25,000, which is a pretty large number for DC2, and we don't typically see numbers anywhere like that, certainly not sustained, and that was causing a kind of a backup that would then have a sort of a hysteresis effect where it took quite a while for the file system to calm down even once the simulation tests were over. The Agro-IBIS processes sort of peak their I/O at about 24 gigabytes per second. That's reads plus writes. And the runs that we did were done at 16-way by 16 processors per node for both 1-way striping and 8-way striping, because we were trying to figure out if maybe the striping would help alleviate the problem. And not surprisingly, it didn't really help very much. Basically, we had lots and lots and lots of files that were being touched lots and lots and lots of time. Striping doesn't solve that problem. Effectively, what we did is we threw this experimental system of 6 HP servers, each packed with 35 terabytes of SSD, and 2 MDS servers with more SSD, and we put this together into a very straightforward Lustre file system that has 0 redundancy, 0 backup. Basically, it's a bare metal system that we hoped would be able to keep up with this code, and at the very least give us something to work with while we're trying to help Dr. Ward's group get their work done and also not cause a lot of sadness with our other users. So the system that we put together itself is basically 2 MDS nodes and the 6 OSS nodes, and each one has an MDT, or in the case of the OSS servers, 2 OSTs, where every MDT or OST are 4 800 gigabyte SSDs basically strapped together in a RAID 0 configuration. So certainly not the kind of file system that you would want to give out to users and have them expect that their data might not die tomorrow. So in this case, we're treating it like a racetrack, and if the racetrack develops a pothole, we're going to repave the whole racetrack. So our, Dr. Board's group knows that this is the case, and he's the only user on the machine right now, on the file system right now, and so that's worked out well. And we haven't had any failures because the system is relatively new, and we're also very lucky here. So, so far so good. We are limited to using DNE1 by our Cray because the Cray is a Lustre 2.5 client. That's not really a particularly big deal, but we do have 2 MDTs, and so it's been, it's just required a little bit more creativity on our part to pull that all together, so that we're using all of the equipment that we have. And then we have 40 gigabit FDR10 InfiniBand to the switch that serves the Cray as well as our other systems. The way that we've gone about analyzing the behavior of the code, especially once we got some of the initial optimizations, or what we hoped would be optimizations, edited into the code and compiled and running, was to use Vampire and ScoreP to do some profiling. And we still have a little bit of an issue with not being able to see into the runtime Lustre activity. So I have the job stats, turned on, and we have counters and that sort of thing, but it's a bit of a challenge to be able to see into the runtime and be able to say, this activity is tied to that activity. And thankfully, we only have one user computing against the system, so any activity, for the most part, certainly any burst of activity, is going to be tied to his work or his group's work, and so we can make that association. But I don't have that data in some of the graphs in the way that I'd like to here. But again, this is a sort of a work in progress. So the initial tests that we did, kind of to some extent showed what we expected would happen. Tests of optimized versus unoptimized code. There were some things that we weren't sure about, and so in hindsight, of course, they make a lot of sense, but they didn't necessarily make a lot of sense at the outset, because we were grasping at straws a little bit and still trying to come to understand what the workflow was. So here I just have a plot that shows for some of the tests that we did with multiple numbers of stripes and different numbers of processes running concurrently. So basically MPI, the number of processes for the MPI code. You can see that effectively they look about the same, and if anything, they look a little worse for, say, the 4-way striping versus the 1-way striping. And so that's shouldn't be a big surprise. If you take something that's not really going to benefit from striping and then you start putting on a lot of extra work onto the file system, you get less out. So at the very least, that didn't really solve our problem. So we tried a couple of strategies to deal with the number of I/O calls that we were seeing. One of them was simply to go into the Fortran code, find out where these excessive opens and closes were happening outside of calls to the NetCDF library, which have their own opens and closes, and basically say, okay, if a file's already open, just leave it open unless it really has to be closed. And it seems really obvious to me now that that's what we'd want to do, but at the time we didn't know how much this would help. And even when we first started testing with it still wasn't terribly obvious how much it might have been helping. The other experiment that we tried was to try different buffer sizes within NetCDF, basically employing a larger buffer cache. Now that, we didn't know what to expect there either, because Lustre has an aggressive caching mechanism itself. And so sometimes when you try to fix something that's already doing a pretty good job fixing itself, you make everything worse. And so we found a sort of sweet spot that we were pretty happy with. We can see the results of using buffer caches on the read side, where we can tell that it's useful. But again, it's something that has to be considered. If you have a file system that's really smart, you don't want to undo the smartness by trying to outsmart it. And so in terms of our read buffers, we have fairly large 4 megabyte buffers for reading, but we decided that it really wasn't helping much on writes. And so we left the buffer size the default for writes. The other thing we did that probably provided the most effective optimization was simply to put as much of the writing as we could on /temp and then bundle the results, and not to be writing out tons and tons of small files that then had to be read back by a post-processing step and stitched together to the Lustre file system, because that was putting a lot of strain on things. And so there's been a lot of work that Cicada has done to try to pull that together and really minimize the post-processing itself. I can show you at least this plot here that gives some idea of what the scaling looks like. These results along the vertical axis are quantized to effectively 1/16 of the original problem size that we were running on various numbers of processors per node. And so the actual quantity of work here is not terribly important, but you can see that we get reasonably good scaling, okay, which is what we expect, because there's hardly any communication in this problem. So it's really all IO pinned. In terms of this plot here, we really want something as flat as we can get. And so what we've seen is that the optimizations that we did were somewhat helpful. The blue is the optimized version. The gold is the unoptimized version. So even on DC2, we have reasonable results. But if you just get a sense of the scale, at 1024 processes, you can see that the blue dot lines up at about 350 seconds. And for the same problem on DCRAM, you can see it's at about 150 seconds. So it's considerably faster. And where we are today is using Vampire to try to get an idea, a much closer look at what our code optimizations are actually doing. And I just want to point out that on here, those that have should be a green background. It's kind of hard to tell, orange versus green, but the bottom pie versus the top pie are optimized versus unoptimized. And if you looked at the runtime view of the percentage of runtime that's dedicated to application versus, say, I/O, the application is dark green, the I/O is yellow, and you can see that at the bottom part we have much less overhead with the I/O. And the purple there is actually showing the read optimizations that we're seeing based on get-R usage calls. So you can see that in the bottom graph there where the purple, the little blips there, those are actually read activity coming back from the file system, whereas before we had what you see there, which just basically looks like a lot of noise. So we're continuing to work on this. Key points to make are that the use of SSD is a good thing, right? I mean, it's a big help because it's fast. Does it have drawbacks? Yeah, it's expensive. We can't afford to make a file system as big as DC2 that's all SSD, but it is helping for this particular case, and hopefully we'll be able to move this problem back to our main file system. The Lustre caching and prefetching seems to work well, and for right now, what we're moving forward with are some implementation of some more fine-grained parallelism in the project or in the code that kind of dives a little bit deeper into the application and tries to effectively reduce the amount of I/O that we have. And then ultimately we plan to move the application back to DC or its successor. And that's what I have. Right, yeah, I'd be happy to answer any questions that you might have offline. You can find my email or just find me tomorrow or later today. Yep, thanks.